Okay, so let's start this talk about this lecture on decision trees. So this is another algorithm that we encounter in machine learning. So K and N, we talked about it. So there are good methods with reasonable theoretical guarantees. I didn't really talk about the theoretical guarantees, but one of the issues is that, but there are some. But the issue is that I just explained is that they are not very explainable. So decision trees, we can think of it as another method, which are also reasonable methods for doing machine learning, and they are more explainable in a sense that we can think about the way that the decision tree works, and you will see very soon, is more like how a human might decide to solve, say, classification problem. And then some variants of decision trees can also be quite competitive. So also it allows us to talk about the idea which is called ensembles, which is one of the important ideas in machine learning. I'm not going to talk about ensembles here in a later lecture, but we use decision trees to create these ensembles. So the other kind of important aspects of this lecture is that I talk a little bit about information theory and the basic concepts of information theory. Decision tree is somehow like an excuse for me to tell you about this for information theory, and we could talk about information theory from many different approaches, but this is a kind of nice connection. And I think what is important for you to learn is basically in this lecture, basic concepts of information theory. So you need to be familiar with them, and also what decision trees are and some simple ways to train them. There is, of course, again, a big literature on theoretical properties of decision trees. There are a lot of variants that I'm not going to talk about, but that's the basic ideas. You need to know what it is. So the idea of decision tree is very simple. Decision tree makes predictions by kind of looking at each attribute and then look at the properties of that attribute, and then based on the result of that, go through different branches of a tree. So maybe the clearest way is to just look at this example. We want to decide whether some image or some data is an orange or a lemon. And what we have is its width and height. So there are two variables that we have. So it's not image, it is just based on the width and height of it. So the decision tree works like this. It looks at the width of it and compares whether it's larger or smaller than 6.5 centimeter. If it is larger, then it looks at its height and then compare it with the value of, say, 9.5 centimeter. And if it is larger, then it would be lemon, otherwise it would be orange. Or if it's no, then we go through this path depending on one of the choices. So this is the decision tree. And the reason I guess it's explainable is because look at each parameter, the attribute separately, and based on the result of it, we say that if this happens, then let's check these other attributes. If not, let's check those other attributes. So this is decision tree. And this is a kind of test example of what happens here. The question that we want to answer, well, this is decision tree. The question is that how we can learn a decision tree in order to be a good classifier for us, for example. Like, what does it mean? It means that what attribute should we check, say, at the root of the tree, and what parameter we should check as a threshold here, like whether it's smaller than 6.5 or 6 or 5 or 4. That number is a parameter of a decision tree that we have to learn. And then for each of its children of the root and any other node, we have to decide what attribute to check, whether we should check height or something else. I mean, here we have 2, so we don't have much choice. But if we had, say, 10 attributes, which one you have to choose, that's the kind of question. and also this value. So learning a decision tree basically means finding the structure of this tree and the values of these attributes. Okay, so if attributes are continuous, as we had in the previous example, we basically split the tree based on whether something is less than or greater than some value. So that value, if it is greater than 6.5, that's the decision we make use for splitting. If we do this, essentially what we do is that we are splitting or we are dividing the input space to different regions. So for example, I think the way it works, so for example, this width 6.5. Let's see if actually this image corresponds to this decision tree or not. So this is 6.5. Okay, so we divide it to left side and right side. If it is yes, so it's larger than that, then we look at the height, and the height would be 9.5. So if it is yes, then it would be lemon as the label that we have. If not, it would be orange. And if we went through the other part of the tree, it gets a different decision or regions for us. So you see that the result of this decision tree is essentially a partition of the input space to these rectangular regions. And then we can also write it more mathematically, saying that decision tree is essentially defining a function. And the function would be f of x would be a function of our regions. We look at whether x belongs to region Ri, and then we multiply it with Wi, the kind of the output here. So if it is the case of regression, Wi would be a real valued number. If it is a classifier, it would be like class 1 or class 0 or something like that. Okay, is this clear? Okay, so what if the attributes are discrete? So suppose it's binary, we can do the same thing, but except of looking at threshold, we check whether something is true or false. So here, this kind of example is that you have this data, you have 12 data points, and then the problem that you want to decide is that whether you want to go to a restaurant or not. And there are some attributes that defines your situation. For example, so it defines, for example, that whether there are alternatives. So whether there is alternative restaurants nearby or not, it's true or false. So whether it's, for example, whether it's Friday or Saturday or not, what is the price, and many other things. And then the label is the question. The label is that whether you have to wait or not. So, so this label is that in this situation there's alternative. There's no bar. It's Friday. You're hungry, and a few other things. You wait. But in another case, you don't wait. So you have this training set. Someone gave it to you, and now what you want to do is make a decision tree that kind of summarizes this information. I mean, the detail, of course, is not important, just like showing that there, if you have binary attributes, how the decision tree would look like. The decision tree would look, one possible decision tree would look like this. That, for example, first we look at the patterns, whether there are none, there are some, or there are full. And there are none, then we don't wait. If there are, because probably the restaurant is not a very good one since nobody else is there. If it is full, then wait time, whether it's more than 60 minutes, we don't wait. Or if it is less than 10 minutes, we wait. So this is one decision tree that summarizes that previous data that we had. So some concept is that internal nodes test attributes like wait time, or there's alternate existing or hungry or not. Then branching is determined by the attribute value, whether it's true or false, here in the discrete case, or in continuous case, whether that attribute is smaller or larger than some thresholds. And then the leaf nodes at the end, these ones, are the outputs or prediction of your decision tree. So we talk about internal node attributes, value of attributes, and leaf nodes. So these are, I guess, the basic concepts that we want to have. So maybe before talking about the learning of these, let's talk about how expressive these are. So if we have discrete decision trees are, if the input is discrete, like binary or like 0, 1, 2, 3, 5, and then output is also discrete, then decision tree can express any function of the input values. So for example, just let's see, for the case of binary, we want to have a decision tree that imitates the behavior of XOR. So we have two attributes, A and B, and based on whether they're false or true, we get different values. So for example, if it is false and true or true or false, XOR of A and B would be true. So this would be a decision tree that computes this attribute. So, or this function. So if it is, say, for example, A is false, we check B. If it is false, then it would be false. If it is true, it would be true. But for example, if it is true and B is also true, so both of them are true, then the output should be false. So this is basically showing that like this logical function, we can represent it. I think it's a good exercise to try to think about how to do it and or. It should be simple. But maybe I try to finish a large part of this lecture, so I skipped them. So also, I guess there are results that showing that if you have continuous input and continuous output case, we can also find a decision tree that can arbitrarily closely approximate that function. So from expressive point of view, these decision trees can be quite expressive. Okay, suppose now for the first step, or learning can be thought of two different steps or two important aspects of it. One is that how to find the structure of the decision tree, and the other is that when we get to we have the structure, which basically means that we have the regions induced by the decision tree, how to select what's the output of that decision tree at that region would be. So suppose we have these regions. So this region, say 1, 2, 3, 4. And now we want to decide what is the true output in this case, in this region 1 should be. Okay, so here, okay, so the blues, the blues are lemons, reds are oranges. So here, what should be the correct decision? Lemon. Here, it should be also orange. What about here? Here, so this case 1 and 4 was easy because all of them are either blue or all of them are red. But what if you have region 3, which you have a combination of both of them? How do you decide? Like here, this answer is orange. But what is the rationale behind that? Okay, so the answer is that have a kind of consensus. Yeah, majority. So our answer, I guess, is majority voting. So yes, basically, we did a majority voting here. Most of them are orange, so it is better to predict that it should be an orange instead of a lemon. So if we have the regions, learning what the decision tree should output is actually an easy question or easy problem. we basically do a decision majority votes between all the labels in that region, as it's written here. So here I'm writing that let's xm1 tm1 to xmk tmk with the training examples that falls into region Rm. So 5, 10, any points. And then for that region, we are computing the majority votes there. And this kind of argmax of this summation is essentially like a mathematical way of writing a majority votes. Okay, so that's good. What about if it's regression? So then the output values are real valued number. In that case, what is a reasonable thing to do? Average. Okay, so there should be the average of points in each region. That's true. So we compute the mean value or average of the targets there. So there was a point that should that t be t to the power of mi. I guess you're referring to this one, I believe. I could use that, but no, I'm kind of optimizing based on some generic t. And then this t for region 1 or region 2 would be different. So it's kind of like defined locally. But it could also, I could write it as t with subscript. Oh, right. Okay, yes, that's right. So that's a good point. So this is here, because I'm using T for labels. So this should be T and I. Okay, okay, thanks. Okay, now if we have the structure of the tree, the problem is easy. But how to find the structure of the tree? The idea here is that we want to find a tree that is simple, but also explains the data well. So this is not very accurate what I mean here by simple. So what does simple tree means? One way to think about it is that a simple tree is a tree that has the minimal number of nodes. So if you can find a smaller tree which is like 10 nodes that explains the data, that would be better than a tree that has, say, 100 nodes and explain the data with the same quality. So this is a little bit imprecise, and because the notion of simple or complex on itself is not a very well-defined thing. So we can define it in different ways. But here the idea is that if you take the idea that simple means that the smallest tree, the smallest number of nodes, then that would be one notion of simple. Okay. The problem is that, okay, so we have this problem that we want to learn the simplest, smallest decision tree, which correctly classify training sets. So this is the goal of finding the structure of the decision tree. The problem is that this is a computationally hard problem. So it's an NP complete problem. So we can't really solve it in practice if the size of trees non-trivially large. So the way that we do it is go through different heuristics. And the heuristic that we use is based on some kind of greedy selection of how to grow the tree. And I explain it soon. But what I want to emphasize at this point is that these are only heuristics, so they don't necessarily find the optimal tree, which means that the smallest tree that classify everything correctly. Because that's NP hard, and if we could solve it with a greedy algorithm, we would be in some form of surprise. So how does the greedy algorithm work. At a very high level, it's like this. That we start from empty decision tree, and then all the data set, and then we split the data set based on some form of best attributes. And then for each part, we do recursively do the same thing. So what does it? Okay, I will explain it more, but basically we start from the roots. We decide which attribute is the best one to check. So we decide maybe dimension, the width of the orange and lemons is the best attribute, and best should be defined. So then based on that, and maybe there's a threshold too, like 6.5. And then based on that, we divide the data set to those with width larger than 6.5, which goes here, and those that are smaller. And then we find the best attribute here, the best attribute here, and then we recursively do these things again and again. Now, of course, the question is that what is the best attribute, how to find the best? And the way that we do it is based on some notion of gain of a split. So gain is defined as based on some change in some criteria based before and after a split. And there are different notions of gain. And I'm going to talk about two of them, and you get a sense of what it means. Okay. So the first definition of best, we have another one later. The first definition is based on accuracy as the criteria, and which means that accuracy is essentially classification error, like what percentage of data points we can correctly classify. So misclassifying error L, the number of incorrect classification, we use it as a criteria, and then we define the gain as change in accuracy before we do the split and after doing the split. I think it would be most clear if with this image. So here we have all data points. There is no split there. So we are at the root. So I don't know the exact number of these oranges and lemons, but suppose that, okay, suppose that there are 60 oranges and 40 lemons. So what is, okay, first of all, what is the best choice here? What label should we choose if we only want to have one decision in the whole region here? Yes, so the answer is orange, because it's 60. So 60 orange is the majority. The best choice is saying orange. So what would be the classification error here if we choose orange? 40%, right? Because for all the lemons, we are saying the wrong thing about them. So we have a 40% error. Now, suppose we divide the region, we choose width as the parameter, and we divide it at these points, like 6.5. So what happens here is that you have two regions now, R1 and R2, and each of them you can do a majority vote. So here, I think the lemons are the majority. Here, the oranges are majority. If you choose, say, lemon on the left side, you make some errors, which are essentially because of existence of some oranges on the left side. So there will be some amount of error. I don't know what percent, what number. And the same on the right-hand side, you make some kind of errors on the lemons. So now you have two regions, each of them with some kind of classification error based on their local decision, like after this split. So the gain in accuracy basically means that how much the accuracy changed before doing this split and after doing that split. And that's called accuracy gain. Yes?
Do we already split the map?
Sorry.
Do we already split the map like in the middle?
No. So that's a good, so the question is that do we always split in the middle? And no, the answer is, so this is just an example. We could split it, for example, at another point. Okay, so for example, we could split here in different dimensions, different values, like all of these are valid splits. And actually, I think it's a good point because we will see that we search in the space of all possible splits and find the best one, which has the most improvement in our accuracy, in our gain, whether it is accuracy gain or the other criteria that I'm going to talk about later. Okay, so I think this is what I described before. So misclassification loss before split is L of R. Now, after a split, I have in the left side of region 1 would be LR, region 2 would be L of R2, L of R1 and L of R2. And then this ratio of R1 divided by R, and we have this ratio of R2 divided by R. Why do we have that? I mean, it might be, it's an obvious question, but I just want you to think about it. Yes, if you have because Ahmad raised his hand.
Yeah, so I guess if a region is larger than the other one, then the error that we have on that region is more important than the smaller region because probably more data is going to occur on that region. So that would be the reason for these fractions, I guess.
Right, yes, so basically, I don't know if you heard it or not, but okay, so if you have different number of data points in different regions, the error in region with larger number of data points would be more important. Maybe just a kind of an example, if I split like this, I mean, here I don't have any error. I can choose orange as my label, but I make a lot of error in the top side. And I need to give more weight in the top side because these are more of the data points. And basically, this is computing, like we are computing the error after split. This is computing what percentage of data points fall within that. So it's kind of conditional probability of, so this would be the conditional error, condition on just focusing on that region. So in order to compute the average error over the whole data point, I need to compute it, I need to multiply it by the probability of a data point being in that region. So this is the idea. So this is before, this is after. And the difference is before and after. So how much accuracy we gain. So what is important here is that I think, as you mentioned, is that we have it, maybe a mute. Is it possible to mute yourself? Someone's, okay. Thanks. So we have different splits based on different parameters. So for example, if you want to only split based on width, we have a lot of different choice of splitting points. So this would be one split. This would be another split. I mean, we have a lot of splitting points here. And if you wanted to split based on height, okay, we have a lot of different splits. And in order to choose the best one, this heuristic says that choose the split which has the highest gain. We have to look at all the possible splits in the data set in the tree that is possible select the one that has the highest gain. So this is, yes.
Is it height and weight for zero? So we have in-state option.
So that's actually a good point. Yes. So if you want to run it computationally, it's very expensive because it's continuous, so you have infinite number of different possibilities. One trick, though, I mean, it's not complete trick. It's, what you can do is that you can only look at the splits that happens at the data points. So just to give you an example, like if the split is here or here, they are the same, doesn't matter. But if you look at the split that passes through this point, and then after that point, that would be the first split that actually changes the regions in any meaningful way. So you can go through all the data points that you have, and for each attribute, look at the split that that data point causes. So, okay, so let me go forward a little bit. So accuracy is not always a good measure of deciding. So, okay, yes, there's a question.
I just think there is a
So what's up? What's up?
I think there is
Oh, there's a question. Okay, yes. Yes, please.
Yes. So my question is, we use the area of these regions as a measure of how probable it would be for a data point to occur in these regions. But maybe sometimes that's not the case. Say we have the width can be from 0 to 10 centimeters, but it is the case that natural oranges have a width that is much more closer to 8, and you never find oranges that are like at 5 centimeters. And then if you draw a decision boundary on, I don't know, close to 5, then the two regions don't actually have the same probability. The one that contains 8 has a higher probability, although they have the same area.
Correctly. Maybe I should clarify that this is not area. So this is R1 divided by R is not the area, but is the number of data points in that area.
Oh, okay. So yeah, I understood that
so,
the wrong way. Thanks.
So this would be, yeah, that's a good clarification that each R essentially, whatever Ri would be the number of data points. So it would be, I think you can think of it as all x's such that xi belongs to region. Maybe I take J. So this is the kind of definition of R, the size of R. Okay, so accuracy is not always a good measure to decide. This is one possibility, but it is not necessarily the best criteria. Why? This is kind of give an example that may convince you that this is not a good one. Suppose we do this decision. So first, in the root, at root, we have 100 lemons and 49 oranges. So any decision, the optimal decision here is that to choose lemons, but there would be 49 divided by 149 chance of error. But now if we do this kind of split, when we get to this region, we are very certain about the actual classification. If you can turn off, mute yourself, that would be great. It would be, thank you. So here in this region, there is we are very certain what is the true label. But here we are not that certain. But at least by doing this kind of division, we reduce the uncertainty for one part of our one region very much. But if you compute this accuracy gain here, so if you do the computation, so we start from 49 divided by 149 minus this calculation, you get an accuracy gain of 0. So this basically says that this split is not necessary. This is not a good split. Even though, at least based on our intuition, we can argue that this is actually a good split because it reduces our uncertainty very much. So we have reduced our uncertainty about whether a fruit is lemon, which is a good thing. So now I'm going to talk about the other criteria, which is we talk about the uncertainty as the criteria to decide whether we do split or not, and or maybe more accurately, gain in the certainty or gain in the reduction of uncertainty to decide the split. Now, of course, the question is how to quantify uncertainty in a kind of precise way. And that's the topic that I'm going to talk about at the next part, which is on information theory. So this basis of information theory, I guess it's 7 minutes past. Some of you, I believe, should leave. So maybe we can stop at this point and continue next time. And maybe I can answer a few questions and we finish the class.